So in this problem, we have this object being propelled up this sort of collar by this force. And we're asked that when our angular position is 90 degrees, which means this, to determine this force F right here, which they mentioned be tangential. That's really important. That means the direction of the force is always tangential to the path. But it's an important distinction. Here we are tangential to the path, but not tangential to my R. So, tangential to the path of the motion of this object, but not the R. And we also want to determine the normal force. So here we are at this origin. Interestingly enough, the origin is not here. And I proved that because of this equation. When I plug in an angle of 0, that means this angular line. And what is the R that comes out at an angle of 0? Well, e to the 0 will equal 1. So I know that even when we're at an angle of 0, we're at a radius, an R value of 1. So long story short, the origin is not here. The origin of this R theta coordinate system is there. Just getting my bearings on the problem. So my object is here, such that my radial line is at a 90-degree angle. My angular position theta is increasing this way. So this right here is my transverse direction. And of course the outwards from the R in the direction of increasing R is my radial direction. And I'm going to deal with the kinematics first. I know that we want to determine force. So we want this, but I need to be able to figure out acceleration information so that we can use Newton's second law to figure out things about our forces. So right now, I'm not going to worry about forces. I'm just going to worry about those kinematic variables, velocity, position, acceleration, that stuff. So let's try to do our velocity. Well, I know the true velocity at this instant of time is always, where is my object pointing at in this direction? That gives us the direction, at least, of the velocity vector, tangent to this path. The velocity vector is always tangent to the path that you're traveling on. So I automatically see that this is not going to be one of those nicer problems where I know the direction of this velocity and I use the right triangle sine cosine tangent to really make it easier to figure out these components as well as this velocity magnitude. Since I don't know the angle, it's not going to be as simple. Let's see if I can try determining these components here. From the picture, they should be positive. Here's my transverse component, and here's my radial component. So they look positive from the picture. So that is what I'm expecting the numbers to agree with that. So let's go with the transverse component first. Looking at the problem description, they give us the rate of change of theta with time, a positive 2 radians per second. Yeah, and since we have this force that is driving this motion going that way, I'm sure that these angles are increasing. I'm sure that our sort of thing is traveling like that, such that those angles are getting bigger, hence the positive. Now, our R coordinate at this time, we can determine that no problem because we're given the fundamental equation of the path. And I want to remember that this angle is given in radians. So instead of plugging in 90 here, I'm going to plug in 90 in radian form, pi over 2, which means that my r value will be, that'll be a 4.81. So I'll make sure I reflect that in the picture. So doing the 4.81 times that 2 gets me a 9.62 as our transverse velocity component, because this is just a smaller part of the velocity. Units will be meters per second. Now again, if I knew this angle right here, everything would be great, because I know this side, I know this angle, and all the other sides of this right triangle would unlock, but I don't know the angle. So I need to figure out my radial component of velocity, which means I need to do the calculus. Here's my r right there. So I'm going to take the derivative of this equation. And what that will give me is the rate of change, instantaneous rate of change, of that r variable. And to perform that derivative here, I'll say it every time, chain rule. Remember, when you see this, you got to pretend like there is some equation inside that theta. An equation where theta is a function of time. And of course, we're not just saying this. As our thing travels here, my theta is going to increase. So there's got to be some equation out there that gives me that as time goes on, it gives me those different theta values. I mean, if theta just didn't change with time, like if our object was traveling this way, like that, our theta would be 0 the whole time, which means it would not change with time. But in this case, it obviously does. So just remember, you're always relating that math back to the actual picture, what's actually happening. So this mystery equation is our inside function. Our outside function is that e. So chain rule is the derivative of the outer function, which is just e times theta, or e to the theta, times the derivative of the inside. Now the derivative of this inside function we don't know, because we don't know what that inside function is. So therefore I just say whatever its derivative is. So plugging in my quantities here, and now my theta at this moment is 90 degrees, pi over 2 in radians, and my rate of change of that theta variable is an increase of 2 radians for every second. So I can math all this out. dr over dt is just written a little quicker as r dot, just another symbol, which really means this quantity. Yeah, just don't forget, when you see these things, just remember to break them down and remember what they really mean. So the r dot that I get is a 9.62 meters per second. And funny enough, this is the same thing we got for the transverse component. So what that says to me is that this angle has to be 45 degrees. When I have a right triangle and both sides are the same, remember, an angle essentially creates the side opposite of it. When I have a small angle, it creates a small side, but when I have a big angle, it creates a big opposite side. So if both of the sides of both the sides of the right triangle are the same, that means the angles that create these sides are the same. And the only way for that to be possible is if they're both 45. Of course, this is 90. So that's how I'm able to just see 45 so quickly. So we'll put that there in case we need it. So now we're going to focus on acceleration. But the thing is, I have no idea which way it is. At least for velocity, I know that it's going to be tangent to the path, to where I am at this instant. But I can't really make any statement like that for acceleration, so I'm just going to get right to crunching out these components. So starting out with the transverse acceleration component, I got the r value, and then I have theta double dot. Remember, that just means how much our angular speed is changing with time at this moment. And since they tell us that that force maintains a constant angular motion, that means that theta dot is a constant and it doesn't change at all. So theta double dot is a 0. 2, r dot we know is 9.62. Theta dot we know is 2. So we can crunch that out and we'll get a positive 38.48. Next up is our radial component, and I need to calculate r double dot, which means I have to take another derivative. Doing that will end me up with r double dot, and to compute it I've got to do the product rule, because I have two quantities, two equations of time getting multiplied by each other. So doing that product rule, I keep the left unchanged and multiply by the derivative of the right equation plus the derivative of the left equation, which we've already walked through, times the right equation unchanged. So this whole thing is a 0 because that theta double dot is a 0. We know our angle, and we know our angular speed. So just crunching that out, that'll get us a positive 19.24. So with that known, and of course we know the r and our angular speed, I can crunch out this radial component. And for that we actually get a 0. So it appears that my true acceleration is only in the positive transverse direction with a magnitude of 38.48. And now that we know this, we can take a look at our forces. So as for our forces here, I know I have the weight going downwards. Mass is 2 kgs, so 2 times 9.81 gets us a 19.62. Next, I know we have this force that's really causing the entire motion, and they say that this force acts tangentially, which means that this force is in this direction. And at first I'm a little worried because I'm thinking we need some sort of angle so we can split this force into its theta and our components. And when it said tangentially, it actually brought me back to when we were talking about the velocity and how the velocity is tangent to the path. And we said that that velocity is actually 45 degrees with that theta axis. So since the force also acts in that tangential to the path direction, this angle is going to be 45. So good, we have an angle for the force, we'll be able to break it down. And I will assume that the normal force is acting in this direction rather than that direction. This is a 90, so this is a 45, and the normal and the force vector make a 90, so this is also a 45. So now we can just do our sum of the forces. In the transverse direction is mass times that acceleration. Remember, positive here is to the left. So this acceleration here is positive. Now, what forces do we have acting in this direction? We have a component of the external force acting to the left. To use cosine to get it. This guy does not act at all in that theta direction. And I gotta use the sine here to get... Actually, hang on. This is positive. Because like I said, left is actually positive here. And this component of the normal force will be the one that's negative. So, minus normal force sine of 45. Alright, two unknowns, one equation here. So I got to move on to my sum of the forces in the radial direction. Now we know there is no acceleration in the radial direction. So this whole right-hand side will be a 0. And as for my forces, I have the weight acting downwards. I have that sine component of that force acting upwards. And the cosine of that normal force also acting upwards, all equal to 0. And with two equations now I can solve for my two unknowns. For my force, I'll get a positive 68.18. And for the normal force, I'll get a negative 40.43. Which means our normal force here is acting in the opposite direction that we assumed it. So these two answers right here are actually not what my book got. So this problem is from the Hibbler Dynamics 13th edition. And I'll show you the solutions page for it. So here's our same problem right here. If you zoom in, and they actually have the same exact free body diagram, everything's the same. If you zoom in on their sum of the forces, it seems like they are, right here would be, they're forgetting the gravity. Where's the gravity? And that's a pretty big mistake right there. I mean, the collar obviously has mass here that we cannot ignore. So we need to account for the gravity, which should be in that negative r direction. So I think I'm correct there. I think the book is incorrect. But all of our other work is matching up with the book. The r dot, the r double dot, 0 for the radial acceleration, 38 point something for the transverse acceleration. So all of our work here is good. So hope everything made sense in this question.